Okay, this will be chapter 15, theories. Big picture of everything and why we're studying this particular topic right now. Acids and bases come in two varieties: strong acid and weak acids, and strong bases and weak bases. When we get into the weak bases and the weak acids, the compounds in solution will function to ionize and will be limited in the degree of ionization and will reach an equilibrium very quickly. So weak acids and weak bases form equilibrium. In aqueous solutions, so that they fit pretty well in the context and sequence of the material we're covering. Having just finished studying the concepts of equilibrium and the issue of the equilibrium constant, we will apply the same concepts to weak acids and weak bases, and when we get there we have to do some other issues also. But we will see that in this section, something like a weak acid, acetic acid, will be something like HC2H3O2, which will have in the front of it what we call an ionizable hydrogen, meaning that it will break away from the rest of the molecule when placed into water. Also, we will see non-ionic hydrogens, which of course will not ionize. And so in aqueous medium, when we put it into water, we find that it begins to ionize and will deliver hydronium ions and acetate ions. But after a short period of time, very short as a matter of fact, the reaction begins to reverse itself and recombine with hydronium ion and the acetate ion, forming the acetic acid. So we have established an equilibrium here in aqueous medium. Now, showing this in one or two forms, this just simply shows the interaction and delivery of a proton. But in actuality, it's HC2H3O2 aqueous reacting with water, in which the proton is transferred over to the oxygen, as shown here, to deliver an hydronium ion, as shown here, plus the acetate ion out here. But to shorten this effort, we consider this to be the H plus ion, and that will be used from here on. But as you see that H plus ion in equations, please understand that it is the hydronium ion. Protons don't float around in solution by themselves, and so the proton would coordinate with the electron pair that's on the oxygen and form the hydronium ion. And we'll learn about this in a moment. That's called a Bronsted acid transferring to a Bronsted base, in which the proton moves over to the reacting element in the reactant side. Okay, so in this analysis of this, if we use this equation, we'll still be looking at, well, what's the extent of the reaction and trying to define the extent of reaction in terms of an ionization constant or an equilibrium constant. The equilibrium constant for acids and bases are, of course, still capital K values, but there'll be Ka's, which are defined as acid ionization constants, or KB's, base ionization constants, as shown here. So when we define the Ka, and you recall that equilibrium constant is extent of reaction, listen very carefully to this. The larger the number, the more stuff it's delivering into ionization. The more ions are being delivered into solution. So the larger the K value, the stronger the acid, or the larger the Kb value, the stronger the base. So that's a very simple analogy that you can use to identify the relative strengths of acids and bases. Look up the K value, and who's got the bigger one will be the stronger of the two. If you're comparing, stronger base would have bigger numbers, stronger acids have bigger numbers, and so forth like that. The analysis of this, either the Ka or the Kb, we'll take the, well, I'll come back up here a little bit more. If you have, and I use the acetic acid, we can write it in some different forms. Of weak acids, let's put it that way. And we'll use acetic acid as an example. I just showed you the acidic hydrogens out front, just like this, is C2H3O2, okay? And when it ionizes, it breaks at the hydrogen, goes to hydronium ion and acetate. Like that. Now, many chemists will abbreviate the anion. And this is the acetate ion, and what they'll do is they'll write an OAC. Because the acetate ion, hydrogen connect at that oxygen, and they'll put an H plus and then an OAC representing the acetate and ionize like this. It just saves pen and pencil, I suppose. But it's a common practice. You'll also see acetic acid written in a graphic form, semi-structural, like this. Like that, with the acidic hydrogen on the end. Sorry. Right here, and you will see this written many times like this. All of these I'm giving you are used widely in the literature, and they show up being identified in problems and what have you. Structurally, there's the acitic acid in terms of its ionizable hydrogen attached to the oxygen, the very most electronegative element. That's what gives us the acid ionization properties, is that the hydrogen's attached to a highly electronegative element. These hydrogens are attached to a poorly electronegative element and form strong bonds right here, so they don't come off. And so, just like the other examples I've shown you, the ionization would lead to this plus H plus. Now these are, again, just examples to show you what will show up in the literature. As I go through the material in this, I will be using those probably more than any of the other two in here in explaining how all this stuff. If we have HOAC, for example, when an equilibrium of H plus plus OAC minus, these represent molar concentrations. And since it is in an equilibrium, you will find all three ions in solution. And so when you calculate a Ka value, it's products over reactants, just like we've been doing. In this context, products over reactants. And these represent molar concentrations of ions, and of course this is the remaining molar concentration of the weak acid. Okay, so the weak bases, and we'll get to this. I'll show you one weak base just to illustrate how this fits into the equilibrium scheme. Ammonium hydroxide, right here. You put ammonium hydroxide into water, it will certainly ionize at the ammonium ion, giving you the ammonium aqueous cation and the hydroxide anion aqueous, and that would be a weak base. In this case, it would be analyzed relative to products over reactants, just like the acid was products over reactants, but this time it would show the ammonium concentration, the hydroxide concentration, and the unionized portion right there. What can be determined from this in the laboratory from information like this are a number of issues. Analysis gives hydrogen ion concentrations, hydroxide ion concentrations, molecular concentrations, base concentrations, pH, pOH, Ka values, Kb values, pKa's, and pKb's. All of that you're about to get into, and how to use this analysis to understand how to determine all of those individual numbers and what they mean and how to apply them in laboratory work. Or theories of acids and bases. Three theories are very dominant in the world of acids and bases. Actually, there are four. One we're not going to get into is called a solvent theory of acids and bases. But the ones we'll be looking at are first the Arrhenius theory of acids and bases, then a theory called the Bronsted-Lowry theory of acids and bases. Has two little dots above the O. Well, I don't know. And then one that's most dominant in organic chemistry is the Lewis acid-base theory. The Arrhenius theory is based upon the presence of hydronium ions and hydroxide ions. Okay. that characterizes in terms of delivering an acid or delivering hydroxides. When we characterize these acids and bases, we characterize them as electrolytes. Acids and bases are electrolytes. Electrolytes are substances which, when put into water, ionize and conduct an electric charge and have the ability to conduct an electric charge. The electrolytic cell consists of a battery, jar, or just a container of aqueous salt solution containing cations and anions. Okay, it could be salt, it could be an acid, hydronium ions, base, hydroxide ions, anions from something else, whatever. They contain an electrode, usually an inert electrode, graphite electrode, like that, and connected to a transformer or a battery. The short side of the symbology represents the negative side. Long side of the symbology represents the positive. Well, if this is negative on this side, this electrode becomes negative. Of course, this one will become positive and will attract the negative ions to it. Positive ions will migrate to the negative side, and the negative ions will, of course, migrate to the positive side. And when these go over, what they do is deposit electrons. Okay? And so this one goes over here and extracts electrons. Like that. So we have a deficiency of electrons over here. And we have a surplus electrons over here. So if we got a surplus of electrons, then you'll have an electron flow. That's good enough. These are, of course, electrodes, anode, cathode, but we'll get to that and later. As acids or bases are electrolytes, we have strong electrolytes would be strong acids and strong bases. Well, strong electrolytes are characterized by 100% ionization.
God bless you.
Okay. Sorry. What's okay? So if these ionize 100%, they do not enter into equilibrium. They do not have an equilibrium constant, or you might say the equilibrium constant is infinite. The strong acids, Arrhenius acids, if you will, include HCl, aqueous, HBr, aqueous, and so forth, HI, HNO3, HClO4, and H2SO4, first ionization step. Now, this is a diprotic acid. So when we talk about first ionization step, we're talking about the ionization of the first hydrogen. And one of the hydrogens remains behind, like that. And then the second ionization step is the bisulfate. That should be 1 minus, sorry. Like that. However, the second ionization is in fact a weak acid ionization because it has a K value. The HSO4 has a K value of 1.1 times 10 to the minus 2, but this one has an infinite K value. Now, why is it infinity? I'll take just any one of these and show you this idea. HCl, 100% ionized, goes to, say, H plus Cl minus. Well, what's the Ka value for it? Well, Ka, if you wrote one, would consist of hydronium ions, chloride ions, divided by HCl ions. Well, if it's 100% ionized, how much HCl do you have in solution? Huh? None. So when we calculate this, regardless of what hydronium ion and HCl are, it's over 0. So you have to have some of the acid compound in solution with the ions that they're delivering in order to generate a Ka value. Okay, so the strong acids, as we talk about them, do not have Ka values, infinite. If you have to give something in terms of that. Well, if these are strong acids, how do we characterize weak acids? Here is a table of weak acids. Let's see if I can get a zoom in for you. Well, this is good enough. Hang on. There you go. That's good enough. Move it over just a fraction. But in these acids, notice that all of the formulas over here have a hydrogen in front. Even though there may be a hydrogen buried back in the formula, I'll bring it down here to acetic acid. You can see acetic acid right there. Right here. This form of acid, how it's being written, is placing the ionizable hydrogen in front of the formula. So it makes it really easy to identify. Here is a diprotic acid. It ionizes in 2 steps. It sends one of the hydrogens and has a bicarbonate. The bicarbonate has its own Ka value. Yeah. This one will have a number over there. Here's your bicarbonate. It too has a different, because that hydrogen's held on tighter than the hydrogen, the first hydrogen coming off of the carbonate. First hydrogen, 4.3 times 10 to the minus 7. 4.8 times 10 to the minus 11. Smaller number, you recall, for the K value says we're not delivering as much product. Isn't that it? You're not delivering. So this would deliver a lot of product, hydrogen, This one, not so much, because it's a smaller number. Bases are compounds which, when placed into water, deliver hydroxide ions into solution. They enter compounds which placed into water will deliver hydroxide ions, and these are divided into strong bases that ionize 100% and weak bases. These ionize less than 100%, like that. So it's important that we identify the strong bases and the weak bases. Now, it's a little bit different in this context when you talk about Arrhenius weak bases, because they will be ammonia derivatives in ammonia. So they're easy to identify. But the strong bases you have to memorize also, but strong bases include group 1A hydroxides and group 2A hydroxides, except beryllium hydroxide. It is not considered a strong base. So if we looked at the collection of group 1, you have lithium, sodium, potassium, rubidium, and cesium. So we'd have lithium hydroxide, where it's -1 hooks up with a +1, or sodium hydroxide, also a 1-to-1, and so forth. But when we look at the group 2 hydroxides, say magnesium is a 1-to-2. And when ionization starts, and it's not going to be a double arrow, magnesium is delivered plus 2 hydroxides. Now, notice the 2 hydroxides. That's going to come into play in some problems in which they'll give you the magnesium concentration, and then ask you to tell you what the hydroxide concentration is going to be. It's going to be twice the magnesium hydroxide. They give you a 0.1. This is easy enough. Say they give you a 0.10 molar magnesium hydroxide. If it's 100% ionized, then this is going to give you 2 times 0.10 molar in OH ions. It doubles in the ionization. You don't read that? Too kind of squirrely. Like that. But you need to spend some time learning the strong bases. They're very straight up and very easy to remember. And when you see one, ionization 100% is very important in analysis of the problem. Okay? When we talk about weak bases, the general definition under the Arrhenius as well as the Bronsted are ammonia and ammonia derivatives and water. Ammonia is an NH3 molecule in a pyramidal structure, if you have to do it that way. And a three-dimensional a electron pair at the top, which carries a partial negative charge. Right there. Which means that if you put it into the presence of a dipole, such as water, it's going to electrostatically attract it. It has an opposites attract effect. So if we take nitrogen like this, and I'm going to put the pair on the right side, and water, which is a dipole, which has a positive end. Of course, the hydroxide is a negative end, and the electron pair is a negative on that side. These two would attract, and you would form an ammonium NH3N bonded to that hydrogen, bonded to the OH. This would be a physical bond. I'm going to dot it, and that be a weaker bond. Well, actually, it's a strong covalent bond. It's a coordinate covalent. Coordinate covalent bond is when both electrons in the bond come from the same element. Both electrons from the same. So nitrogen sending both of its electrons into the hydrogen there and forming a strong bond. The outcome of this is ammonium hydroxide, NH4, or here with an OH like that. So it is usually written NH4OH like that. And when it's illustrated in terms of its ionization, it breaks after the NH4 right here and forms the ammonium ion and the hydroxide ion like that. The complete reactive illustration would be NH3 gas plus H2O liquid goes to NH4OH aqueous, should put, illustrates to NH4 plus OH minus like that. Now, in reality, this is the weak base in itself. So when you get an exam, which of the following is a weak base, and you see B choice is NH3, that's the answer. Because when you put it into water, it'll react with water and form the hydroxide, which would ionize like this. However, if you tried to isolate an hydroxide of this ammonia, you couldn't do it. It would break back to a gas of ammonia and water. So it's just a characterization. What it is. Now, that's ammonia. What are ammonia derivatives? These are ammonia molecules with some organic or structural fragment replacing one of the hydrogens, or all of the hydrogens, 1, 2, or all 3. So if it is ammonia, say like this, make this up some, and I break off one of the hydrogens and make a molecule, say it has a CH3 group over here, this is an ammonia derivative. The fragment that's attached to that nitrogen is collectively and universally called an alkyl group. because it's a hydrocarbon group. And in this individual case, we're talking a methyl group. And it is 3 hydrogens and a pair of electrons, which forms the bond in that context. And on the end, it hooks up wherever it needs to hook up. Well, the ammonia derivatives, the ammonia derivatives, thank you, sir, are collectively called amines. Okay. Now, the chemistry and physics of the ammonia derivatives, I'm going to leave the broader spectrum idea. I'm going to leave until you get to organic chemistry and you can learn thousands of reactions to go with them then. But the present issue is the ammonia derivatives function just like ammonia does. You drop an ammonia derivative in water, the electron pair is going to react with water and form a weak base by the coordinate covalent bond. This compound is methylamine. That's it, right there. It's got that. The only difference between that and ammonia is, of course, we put the CH3 group on there. So when you put this in water, that electron pair is going to hook up with one of the hydrogens in there, and you're going to increase, watch this. That's going to go from a 2 to a 3 right there, and it's going to simply be written like that with an OH on it. And it ionizes right through that hydroxide, and you will get your weak base ionization just like that. And so we would use that fragment, products over reactants, and that'll give you some numbers. You got so much OH, so much methylammonium ion and methylammonium hydroxide in solution. So it functions the same way as the ammonia does, except you just got some kind of fragment hanging off of there. It does have different chemical and reactive properties because of the fragment, but that's not part of our story today. It's simply how does the ammonia and ammonia derivatives enter the world of acids and bases, how are they dealt with in context like this. Okay, the second theory of acids and bases is the Bronsted-Lowering theory. I can't remember if I may have mentioned this before. A Bronsted acid and a Bronsted base require a reaction to be defined. A Bronsted acid has a proton, an ionizable proton that can be donated to a Bronsted base that has some fragment that can receive the proton that's being transferred. So as a Bronsted acid it's a proton donor. As a Bronsted base, it's a proton acceptor. That's how we characterize it. Well, typically, if a proton has a plus charge, what's going to be trying to accept a plus charge? Something that has a negative charge, anions. So typically, you're going to be transferring a proton to an anion in the context of what this reaction is telling you. Now, this leads us to the rule of proton transfer in Bronsted-Lowry reactions. Okay, now this can be couched in different ways depending on what constants you're using, but this one will fit here. An acid, okay, will transfer its proton to the anion of a weaker acid. This is a critical statement in your understanding of the behavior of acids and bases as we go forward. It is a critical comment and statement in terms of why certain acid-base reactions occur. It will not transfer a proton to an anion of a stronger acid because the proton prefers to be ionized from a stronger acid. You can write this in the context of H anion like this, plus say some base negative. This would transfer to that base, you can do it like that, to form H base plus an anion that's not strong enough to hold that hydrogen. It's transferring, here is an acid that's transferring its proton to an anion of a weaker acid. So when the products show up with the hydrogen attached over here, that's going to be a weaker acid than the one the hydrogen left. This is a stronger acid. That H anion on there. Well, there are many proton transfer reactions based upon how strong the anion is. In the reaction right here, the base in here being an anion is referred to as a conjugate base. Of the acid. And this acid over here is called a conjugate acid of that original base. Now, the conjugate base is, you'll find it in the literature and in your studies to be far more dominant in things that are going on than will the conjugate acid. Okay? Collectively, see that? Any anion is a conjugate base because it's got a conjugate acid somewhere. You stick a hydrogen on it. Any anion will absorb hydrogen. Okay, that's a conjugate acid of whatever anion you had. Right there. Well, there are many of these. That's too much. Get it or not, guys. So in this table, you can pick any acid that you wish over here and make a product by transferring the hydrogen to any compound anion, conjugate base, to the right and below it. But you cannot form a product by transferring the hydrogen above it, because it would form a weaker bond than the one it left. And the natural order of things is to form stronger. So we begin the Lewis acid-base theory. In the Lewis acid-base theory, one can generally state that all molecules can be acids or bases depending on their electronegative character. So the Lewis acids and Lewis bases are defined in terms of two things: A, electronegative character, and ability, B, well, ability to donate or accept electron pairs. In that, we say that a Lewis acid, by definition, is an electron pair acceptor. I'll show you in a minute. And a Lewis base, by definition, is an electron pair donor. So when we look at a molecule, we want to look at it in terms of, well, can it accept an electron pair? Well, let's take ammonia again. We've already talked about ammonia in terms of an electron pair right there. And so, of course, now begins the understanding and drawing back on some of the geometry from Chem 1. But ammonia has an electron pair, and I've already noticed that it is a negative character. Why? Because of electronegativity. All right? And the fact that you have electrons sitting there that are non-bonded. A very negative character. Now, polarity in bond structures also has positive and negative characteristics. Take carbon double bonded to oxygen, for example. Like that. This is a dipole, strongly dipole, and it's a dipole toward the oxygen, in that you have the more electronegative end of this dipole is on oxygen. What's electronegativity to begin with? Anybody? Sorry. Who's going to attract electrons with a greater force? Number 9 or the number 5? There are 9 positive charges will attract stronger than 5 positive charges. Yes?
Yes.
That end of the row is the more electronegative. Yeah. So the further to the right you go, the more electronegative. And they will be attracting strongly the electron cloud. So when we look at a bond like this, where is carbon on the periodic table versus where is oxygen on the periodic table? Here is carbon, and down here is oxygen. Well, here, carbon here. So oxygen's pulling strongly to this end, and it's uncovering the nucleus. That's the way I think about it. It's worked for years. Uncovering slightly the nucleus of the carbon and leaving it slightly positive. So you got what they call a positive center in that structure. It says positive center right here. And so the negative center will be attracted to the positive center, and a coordinate covalent bond will result in this. Actually, a pair of electrons will jump out. That's not important to you right now. And will form a bond right there. The donator, ammonia donating its electron pair in there, is the Lewis base. And the structure here will become a dipole in itself, not important, will be the Lewis acid. The point is, what reacted here is not a hydrogen or an hydroxide, is the point I'm trying to make. So when we're talking about acids, Lewis acids and Lewis bases, we're talking about Lewis acid, Lewis base reactions that do not involve hydrogen and hydroxide. Now that's as far as I'm going to go with the Lewis acid base theory. In organic chemistry, you will be carried way into the issue. But it all revolves around the concept of electron pair donating and electron pair accepting. And once you get oriented with that and understand the concept relative to electronegativity, it's always positives looking for negatives through the whole course. Terminology and stuff just builds exponentially. But it's still positives looking for negatives all the way through the course. Sodium hydride, and then I throw in something like this, like that. That's dimethyl ether. Well, that's not important, but that is. And you see an electron pair sitting in there. Oh, let's see, Lewis base. And what's it going? It's negative, and it's going to be looking for Lewis positives. And the reaction goes on and forms all kind of organic this, that, and others. That's what drives the reactions. Strength of Lewis acid-base structures. The greater the electronegativity, the weaker the base. I'll say of central element, the weaker the Lewis base. Okay, I'm going to draw a series here. Carbon's been ionized, but it has a electron pair sitting there. Anion, carbanion as it's called. And then we'll have nitrogen sitting right here like this. Then we'll have oxygen with its structure like this, and then we'll have a halogen, say fluoride. Let's put fluoride in the sequence. From left to right in this sequence, we have increasing electronegativity. What that means in increasing electronegativity from left to right, the strength at which the electron pair is held on to the central element is increasing. So we have increasing strength of holding electron pair. In other words, the electron pair on carbon down here would be donated very easily. And the electron pair on the fluoride down here is difficult to donate. In terms of strength of Lewis base here, the one that donates easiest is the stronger base. So we have a stronger Lewis base here and a weaker Lewis base here. Now, what does this mean in the big picture? A stronger Lewis base means this is easy to donate, so it's going to form a stronger bond. And that means it reacts faster. This one, in terms of weaker Lewis bases, forms a weak bond, will break easy and react slowly. If you can remember that as you go into your next level, your understanding of organic chemical reactions will exponentially increase very quickly. That's the simplicity of it. I wish you well.